Hello physics students. In this video, we're going to be doing a lab on simple harmonic motion. Now at this point, you should have already printed out all the lab sheets, pages 1 through 4. You're going to need all the sheets for your data, your calculations, and answering the questions of the lab. Now, if you remember from the simple harmonic motion video lesson, simple harmonic motion is a smooth kind of vibration. Something has to be going back and forth in a very smooth fashion, not in a jarred fashion. The two kinds of oscillators that we're going to be studying in this experiment are, one, the pendulum in part 1, and then in part 2, a mass on a spring oscillating up and down. So I've already set up the pendulum stand and the pendulum on the pendulum clamp here. Remember, pendulum is just a mass on the end of a spring, on the end of a string, a long string compared to the size of the object. And I've made it exactly a half a meter from here to the center of mass of the pendulum. So half of a meter. What we're going to do is determine the period. Now, of course, what I could do is I could just set this into motion, into oscillation, and time it with a stopwatch. Well, we'll do that. We'll get to that. But first, what we're going to do is we're actually going to calculate the period predicted from physics formulas that we learned in the simple harmonic motion video lesson. So let's do that now. So we're going to begin by calculating the period of a pendulum with a length of 0.5 meters, as I said, right here in this space on your lab sheet. Now, this formula that you're going to use is not on the reference table on any of the pages. So you don't look it up there. You have to go back into your notes on the first day of this, the first video lesson of this topic on simple harmonic motion. I wrote down on the board the period of a pendulum on a string. Write down that formula. Remember, as always, you have to start your calculations by writing out the formula. Plug in all the relevant data with units and with units, and then get the value by punching the numbers on your calculator. So go ahead and do that calculation now. Now that you've calculated what the period should be according to the formula we learned in class, what we're going to do is we're going to time what it actually is when I set this into oscillation. Now remember from the lesson for pendulum, I can't get have the oscillation, a large oscillation. Only for the pendulum, you have to keep the amplitude relatively small. So I'll just set it into oscillation like this. The other problem is that if I time one vibration, it's not going to be very accurate because humans have a reaction time. The stopwatch is not very accurate. So what I'm going to do is time 10 oscillations, and then we'll figure out from that information the time for one vibration, in other words, the period. So I'm going to start here and go start. 1 oscillation, 2 oscillations, 3 oscillations, 4, 5, 6, 7, 8, 9, 10. Okay, so I got 14.25 seconds. I'm going to write that on the data sheet over here, 14.25. And then I'm going to later calculate the time for one oscillation. Of course, you're going to get your own data assigned to you for the period of 10 or the time of 10 oscillations, and then you'll figure out your own period. So look that up in the Google Sheet, write it down in space number 3. So here's the time I just measured for 10 oscillations. Again, you need to figure out the time, the period, which is just for one oscillation. So again, you're getting your own value for 10 oscillations of Google Stream, and you're calculating this value here. Go ahead and calculate that now. Now, in a perfect experiment, these two values would be the same. But obviously they're not going to be because experiments have error. So in this box, you're going to calculate the percent error between these two values. This you're going to consider the accepted value. Now you don't have to write the formula out here, but just for those of you who might not remember, I'll put accepted minus experimental over accepted again, don't write the formula out. Just go ahead and calculate with the numbers because there isn't much space here. And then you multiply that by 100%. So go ahead and put your numbers directly here without a formula and then calculate the percent. So go ahead and make that calculation now. Okay, so now the next thing that we're going to do is we're going to go and backtrack. So this formula we plugged in this part, the length for 0.5 meters, we figured out the period. Now what we're going to do is we're going to assume a length of 1.25 seconds. And then we're going to calculate what the length should be to make a period of exactly that long. So we're going to start with the same formula. And again, you need to look that up, write out the formula. And then the 1.25 seconds you're going to put on this side, and then you're going to do algebra, maybe more than one step, and calculate the length that you need to make that exact period. So go ahead and make that calculation now. Now what we're going to do is actually measure what that period is for that length. We're going to set up the pendulum this length, and we're going to see if it comes out to 1.25. So that's what we're going to do now. So now what I need to do is adjust this string length to the length that you just calculated. So I'm not going to tell you what it is because you're supposed to calculate that, but I will just set it up without telling you what the proper distance is. Again, you'll calculate it yourself. Okay, a little tricky by myself. Let's see, somewhere around. There. So I have it adjusted to the right length. Now what I want to do is set it into oscillation. I could just give it a little tap like that. It's in simple harmonic motion. And I'm going to, again, time 10 vibrations to figure out the period or the time of one vibration. So I'll start over here. Ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I got 12.54 seconds. I'm going to write that down. Again, you're going to look up your own time in the Google stream and record the time, not for the 10 vibrations that I've assigned you, but again, the time for just one vibration. So let's move on with the calculations. So that was the pendulum part of the experiment. Now what we're going to do is move on to part 2, where we're going to study the other kind of oscillator that we learned in the simple harmonic motion video lesson. That is a mass on a spring. So let me put away the pendulum. So if I take a spring like this and put a mass on that spring, I can set that into simple harmonic motion just by giving it a little nudge up or down, and then you see that smooth vibration up or down. We're going to calculate the period from the formula that we learned in the video lesson, and then we're going to measure it with a stopwatch so we could compare the two values. Now, if you look up the formula for the period of a mass on a spring, again, remember, that is not on the reference table. So you got to look up that formula in your notes for T equals, and then you look at that formula, you'll see that there are two variables that affect the period. One is the mass of the object oscillating, and two, the spring constant, the tightness of the spring. So the mass is easy to determine because it's stamped right on this metal block right here. But the spring constant, we actually have to calculate that and determine it from measurements because it's not stamped on the spring. And also what we're going to be doing is we're going to be varying the spring constant, and the way we do that, we can achieve that, is by just getting another spring. So we'll be varying the spring constant, in other words, determining the spring constant for these two springs, and then varying the mass by just hanging different metal blocks on each particular spring. So, the spring constant. There are spaces in your lab sheet right here to determine the spring constant, so that's where we're going to be working right now. So the way we calculate the spring constant is a formula that actually is on the reference table. It relates spring force to spring displacement and spring constant. I'm not going to tell you what that formula is because at this point in the course, you need to be getting good at finding all the formulas on the reference table. So you find that formula for spring force, spring constant, spring displacement. So the force we can get by simply hanging a 1 kilogram block on a particular spring. Now the 1 kilogram is not a force, that's the mass. But the mass generates a certain force. I'll give you a hint. What is the force? What do we call this force that pulls this down? Okay, so you need to figure out the newtons, the force on 1 kilogram, because that's what's going to be stretching this spring. We'll plug that force into the formula and also spring displacement. But what is spring displacement? Spring displacement is not how long the spring is, it's how much longer it gets. So like here, this is the equilibrium position of no spring displacement, right where the tip of my finger is. And when I let this go, the displacement is now from here where the spring started to where it ended, the distance between my two fingers. But fingers are kind of like they move around, they're not very precise. So there's a better way to determine the spring displacement other than putting fingers like this. One thing we could do is measure the length of the spring before I put the load on it and then measure the length of the spring after I put the load on it and figure out the spring displacement from those two numbers. So for the short spring, which is the one we're going to begin with, I will measure the spring length now in its unloaded condition. And I get about, I think it looks like 8.9, or is it 8.9? Let's try again. Yeah, 8.9 centimeters. So let me write that down. On my lab sheet, but remember, you always look up your own values. So look up on the lab sheet what your spring length for the short spring is without a load on it. And then you also have to convert it to meters. All distances need to be in meters. I'm going to hang the load on it and just sort of let it come to equilibrium, and I'll measure the new length. The new length with the load is about 25.1. So let me write that down. Again, you're getting your own value and converting it to meters. Okay, so now that I have my measurements for the short spring, let's calculate the spring constant of this short spring. So here are the measurements that I just took. And the first thing that you're going to do is with those two measurements, figure out what the spring displacement is. Now, in this case, there's no formula necessary. Just do something with these numbers, a math operation. I'm not going to tell you what to do with these numbers, but what you want to find out is the displacement, how much longer the spring got, and record that in meters, but show what you're doing. Maybe you multiply these numbers or divide them or add them or subtract them. Whatever you're doing to those numbers, show that without a formula, just do it and then calculate what the spring displacement is for your data. So go ahead and do that now. So you have spring displacement. The other thing that you have is the force. This you don't need a formula again. But what I want you to do is figure out the force on that 1 kilogram in newtons. You could just write the answer out. You don't even need to show how you calculate it. Just show the number of newtons on 1 kilogram. Go ahead and do that now. Now, in the space that's left, you're going to fit in the formula that relates spring force, spring displacement, and spring constant. Again, I mentioned it, it's already, it's somewhere on the reference table here. Go get your reference table, find the formula, write it out, plug the data in, and then solve for spring constant, answer and units. So go ahead and make that calculation now. Okay, so again, no formula necessary here, but a formula and the three-step solution necessary for this one here. Now time to repeat the same procedure for the long spring. Well, this looks longer now, but of course it's only because the load is on it. So I'm going to first measure the length of the spring without a load on it. And I get about 19.1 centimeters. So let me write that down. 19.1 centimeters. All right, now let's put the load on it. Again, the displacement will be from this point to this point. So I'll measure the length of the spring now in this situation. And maybe I'll hold it up here. I get about 49.5 centimeters. So again, you're getting your two measurements from the Google Stream, and let's move on now to calculating the spring constant for this spring. So we're going to repeat that same process that we did with the short spring, but now with the data for the long spring. So the first thing that we need to do is from the data, this is my data, but from your data in the Google Stream, you're going to want to calculate the spring displacement with these two numbers. Again, no formula necessary, but I want you to write out what you're doing with these two numbers. Are you adding them, multiplying them, subtracting them, or dividing? So you're going to have your two numbers here and the math operation that you are doing on them, and you're going to get the answer for the spring displacement, how much longer that spring got when it had the load on it. So go ahead and do that now. You're also going to determine what the force is. You don't have to do any calculations here. You could just write the number of newtons. Remember, it was 1 kilogram, and that created a certain amount of newtons because of some reason why it went down. Go ahead and write out the number of newtons of 1 kilogram now. And then finally, here's where you're going to look up a formula on the reference table for the spring, relating spring force, spring displacement, and spring constant. And so you'll write out the formula here. You're going to plug in your numbers with units. And then when you're all done, you're going to have a spring constant value and the units of spring constant. So go ahead and make that calculation now. All right, the next part. What we're going to do, now that we have the spring constants and the masses, we're going to start calculating the period, but of what spring and of what mass. So the first thing we're going to do is predict which spring, mass-spring combination will produce the smallest period, and we'll calculate the theoretical period. Now remember, there is a formula for the period of a mass on a spring that is not on the reference table. You have to go back to your notes for simple harmonic motion, the very first video lesson of this topic. Write out the formula. Look at the formula, study it. And you have to think, will a big mass or a small mass produce a small period? And will a big spring constant or a small spring constant produce a small period t? Again, you're just analyzing the formula. And there are 4 combinations you could make. I guess I wrote a little too big here, but you could have the short spring with either the 0.5 kilogram or the 1 kilogram, or you could have the long spring with the same 2 masses. So short 0.5, short 1 kilogram, long 0.5, long 1 kilogram. Again, figure out what makes the smallest period, which of these combinations. Do that, and then plug those values, the proper spring constant and the proper mass. 3 steps here. This is the formula, right? Just all symbols. This is the data, the right data with the units, and then your answer for the period of that combination. So go ahead and make that calculation now. So now I need to measure the period for the combination of spring mass that generates, as we said, the smallest period, but I don't want to give away the answer. If, in other words, I pick a certain mass in a certain spring, then you'll be able to go back and fix in case you made a mistake in the previous step. So what I'm going to do is I'm just going to put together both springs like this, just to show you how you go about measuring the period, but I'm not giving anything away because I'm using both the springs. And I'll use neither of the masses. I'll use a 200-gram mass like this. Well, maybe I'll make it 400, make a little, yeah, that's good. So I'm using none of the combinations. But what I do is if I did set it up with the right combination to measure the period, this is how I would do it. So that's all I want to do is demonstrate how the period is actually measured for a mass on a spring. All I need to do is give it a nudge up or down. Doesn't need to be a big nudge because then it just starts going kind of chaotic. And now it's in simple harmonic motion. Again, it's independent of the amplitude, so I could use any size amplitude I wanted, a little vibration or a big vibration, same period. I'm going to time, as before, 10 oscillations to improve the precision of the measurement. So maybe I'll start at the top. So when it gets to the top, so start. Oh, I wasn't that accurate. So start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I got 8.95 seconds for 10 oscillations. In the Google Stream, I'll give you your own time for 10 oscillations. You need to figure out the time for one oscillation and record that into your data sheet. So I just wrote down any time here, but again, you're getting your time from the Google Stream. This is again for 10 oscillations, so it is not the period. You need to find the period from this, in other words, the time for one oscillation. So go ahead, retrieve your value and record the period for one oscillation now. Go ahead and do that now. And then what we have to do is calculate the percent error. And so that's what we're going to do in this box. Of course, these in theory should be the same, but they're of course not going to be because it's an experiment, there's always error. This is the accepted value. And so what you'll want to do is do accepted minus experiment over accepted. Oops, that should be absolute value, times 100%. You don't have to write out the formula for percent error. I'm not that picky with that. And just, put your numbers directly here and calculate a percent. So go ahead and make that calculation now. All right, so we're going on. I decided that we're going to skip this part here and we're going to move right on to this here, steps 6 and 7. So remember, in this part of the lab, what we did is we predicted what was the combination that was the smallest period. What we're going to do is now predict which combination produces the largest period. So again, there are 4 possibilities. So first of all, write down the formula for the period of a mass on a spring. Do that right here. Just formula from the notes, not on the reference table. And then think about, look at that formula where mass is and where spring constant is. And look at the spring constants of each of the springs and decide, do you want the short spring with the 0.5 kilograms or the short with the 1 kilogram? Or do you want the long spring with the 0.5 kilograms or the long with the 1 kilogram? One of these 4 is the correct combination to produce the longest period. Study the data, the spring constants, the masses, and the formula. Make the decision. Go ahead and do that now. Now what you're going to do is take whatever combination you decided, plug the data for that mass and that spring constant in the formula, punch it on a calculator, and get an answer of some number of seconds. So go ahead and make that calculation now. Okay, so now we need to test the calculation that you just made Again, I don't want to give away the answer, so I just decided to take the short spring and put 1,500 grams on it. So this is not the combination, obviously, because it's either one or the other, not both together. But again, I just want to show you how I'm going to make the measurement of the period of oscillation without giving away the answer of what combination of spring mass to produce the longest period. So I'll just give a little nudge here, and I'm going to time again 10 oscillations. So maybe I'll start timing at the bottom now. So start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I got 9.89. Again, you're going to get your own measurement for 10 oscillations, figure out the time for one oscillation, record that in your data sheet. So I just wrote down a time 11.15. Again, you're going to get your value from the Google Stream. This is the time for 10 oscillations. Once again, you need the time for one oscillation. So go ahead from the Google Stream data, calculate the time for one oscillation. Go ahead and do that now. And the last calculation we're going to do here for this lab is the percent error. So again, this is like the accepted value. This is the experimental value. And so percent error, you'll take the absolute value of the accepted value minus the experimental all over the accepted value times 100%. I guess that was a little sloppy there. But again, no formula necessary, just plug in numbers and get an answer for a percent. So go ahead and make your percent error calculation now. All right, so as I said, that's it for calculations. There are questions though. So here they are. This. All right, so the first question, what happens to the length of the pendulum if the period quadruples? So look at the formula, and what you will say is you'll answer this length times or divided by whatever it is, some number. So again, this is one of those questions where you look at the formula for patterns and figure out you want the period to quadruple on the left side. What do you have to do to the length? So go ahead and answer that question now. Number 2, if you took the pendulum of step 2 to the moon, would the period be greater than or less than the value you measured? Explain using the equation. So what I would recommend, or what I'll say is necessary, write out the formula for the period of a pendulum. And then you would say less or more. So that's the second thing, one of them, obviously not both. I guess you could say the same, but I'll just tell you it's not the same. It's either less or more. And then an explanation. You might want to say because something changes in the formula, and is it in the numerator or the denominator, and then does that factor get bigger or smaller, and then what does that do to the period based on whether it's in the numerator or denominator? So go ahead and answer that question now with all those parts of the answer. All right, number 3 is like a practice, something you might encounter on a Regents, a multiple choice question. Which will produce the greatest period? Something with a small spring constant or big spring constant? Something with a small mass or big mass? It's one of these, A, B, C, D. So go ahead and pick your answer now. And finally, the last question. The equation for the period of a mass on a spring assumes the spring has no mass. This is clearly not true. All right, the spring has mass, it's made of metal. Based on this fact, is the time predicted by the formula greater than or less than the actual period one would observe in the experiment? Explain using the formula for the period of a mass on a spring and the fact that there is extra mass present in the spring itself. So what I would recommend is you start by writing out the formula for the mass on a spring period. Again, you used it in the lab already. And then you would say that the time predicted by the formula is, and then you're going to say greater or less than the measured value because mass, and you might say like where it is in the formula and what does that extra mass do in real life to the period, because again, we're not including it in our calculation, but it is there in real life, so you're going to answer based on that. So go ahead and answer that question now. That's the end of our lab video. I hope you enjoyed the experiment. I hope you enjoyed the analysis, the physics. I'll see you in the next physics video.